Since we have seen this for insertion sort, right? We have already seen that if the length of an array is equal to n, then the best case time complexity of an insertion sort algorithm is an plus b. And here a and b are the constants. And the worst case time complexity of an insertion sort algorithm is a dash n square plus b dash n plus c dash, and where a dash, b dash, c dash are the constant. So when it comes to the space complexity, whether it's a best case or the worst case, here we are going to use the 3 extra variables. Now in the next few videos, we will learn various mathematical notation, but I will go into the mathematical details from the next video onwards. But for now, I'm going to introduce one of the simplest and the most commonly used notation called a big O notation. Now let me explain what that means intuitively. Right? So if you think about it, the time complexity of an insertion sort algorithm, both a best case and the worst case, changes as the length of an input array changes. As my value of n changes, the best case and the worst case will get changes. That is, as my value of n or the input size increases, by the way, I'm following this notation, right? So when I say n increases, the meaning here is I'm just writing down as n upward arrow. When I say n decreases, I'm using the downward arrow. Or if I say n increases a lot, so I'm going to use this notation. And if I say n decreases a lot, so I'm just using the 2 downward arrows. So this is the just simple way to explain growth instead of writing the inequalities every time. Right? Now let's go into the details. As the value of n increases, let me write it down here. So as my value of n increases or the input size increases, remember again, so here a, b, a dash, b dash, c dash. So these all are my constant value. Now let's focus on the best case expression first. So what is my best case time complexity? The best case time complexity is an plus b. Right? So as my value of n increases, this value is also getting increases. So I can also write this expression as an plus b into 1, right? And here a and b are the constant. So if you ignore a and b, right? So what the values will remain here? So we have n and 1. These are the values are remaining. Similarly, if you look at the worst case expression, so what is my worst case expression? A dash n square plus b dash n plus c dash. If you ignore a dash, b dash, and again I have 1 here, right? So if I ignore a dash, b dash, c dash, what are the values will remain here in this particular expression? I have n square, n and 1. Now let's analyze how these terms grow as the value of n increases or the input value is increases. First, let's consider the best case, right? So here a and b are the constant. So what are the values are left in this expression? We have n and 1. So as the value of n increases and 1 does not change, again 1 is also a constant here. So which value will get increases? N will get increases. So the growth is dominated by n here. So therefore, I would say that the best case time complexity of an insertion sort algorithm, I'm going to use this notation called order of n. So I'm just writing down as a big O of n. So I will define this mathematically in the next few videos. For now, just understand this intuitively. Once after ignoring the constant, and here I'm just focusing on how the function grows when the value of n is increases. Similarly, let's look at the worst case. So this is my worst case expression, right? So after ignoring the constant, I have n square, n and 1 are left here. As my value of n increases, 1 will does not change. This is also a constant, and obviously n also will get increases. And what about an n square term? So this increases much faster than n here. So if I increases the value of n, which of these terms increases a lot? The term n square will increases a lot. So let me take a simple example to understand. Suppose my value of n is equal to 10, and what is the value of n square? N square will be 100. Suppose, now suppose if my value of n is equal to 100, what is the value of n square here? N square will be 10,000 here, 100 into 100, 10 power 4. So as here n increased by 10 times, n square increased by 100 times, right? So here I'm changing the value of n from 10 to 100. What about my n square value? N square term is getting increased by 100 times, right? So here 10 times and here 100 times, right? So that is what we can easily notice from this example, right? So n square term grows much faster than n here, right? Obviously n also increases, but this term increases much faster than n. So among these three terms, n square, n and 1, the term that grows faster as n increases here is n square. So the worst case time complexity in terms of order is order of n square. So the time complexity of an insertion sort algorithm in the worst case, I'm going to written as order of n square. So even though the expression contains n1 n square, but the term n square dominates the growth. So this is the most often notation used a lot in the whole of practical algorithms, and I will define mathematically in the next video. So the notation here is the big one notation. Now let's look at the space complexity. So in terms of the space complexity, we are using only three variables, right? So we are using only three variables. What are those three variables? Key, I and j. So here 3 is a constant value. So here 3 is a constant. So there is no n term in case of a space complexity, right? So as my value of n increases, as my input size increases, the space usage doesn't change. So therefore, the space complexity of an insertion sort algorithm will be order of 1. So this means the space used is the constant and independent of my input size n here. So this is my independent. So whenever I just written order of 1 means these are independent of my input size n here. So in a summary, I would say that the best case time complexity is order of n, and the worst case time complexity of an insertion sort algorithm is order of n square, and the space complexity of an algorithm is a constant time. Intuitively, or what is the meaning of order of n here, right? So order of n means the running time increases, right? The running time of an algorithm increases proportionally with the input size. So if my value of n increases, my time is also getting increases proportionally. So what about an order of n square means here? Order of n square means running time increases proportionally with the square of that input size, right? Even if you want, you can verify this, right? So I'm just taking the worst case time complexity. So a dash n square plus b dash n plus 1, sorry, c, right? So let's assume c dash. So let's assume a dash value is 1, b dash value is 1, and c dash value is 1. So in the worst case, the expression become n square plus n plus 1, because here I have c dash into 1. Now, if my value of n is equal to 10, right, the value will be, if I substitute this value into my equation, the value will be 100 plus 10 plus 1, which is equal to 111. What if I substitute the value of n is equal to 100 into my expression, the value will be 100 square will be 10,000 plus n value will be 100 plus 1, so which is equal to 10,101, right? So as the value of n increased from 10 to 100, right, most of the increase from, so this value getting increased from 111 to 10,101 came from so the biggest value came from the n square term, so not from the value of n or 1, right? So that is why we say the time complexity is order of n square here. So the order of 1 means it doesn't change the It doesn't change as the input size increases. So in the next few videos, I will define the big O notation mathematically, and we will go much deeper into it, right?